So we're going to finish up section 6 in chapter 3. So we had these different particular kinds of arguments that we went through. So these are the two premises and the conclusion, and these were all valid arguments. Again, we don't have to memorize the Latin names or anything like that. But it turns out if you had an argument like this one, and if you can show that it's one of these already determined standard arguments, you don't have to go through the whole process of creating a truth table, unless I tell you to do it. But so what we're going to do is we're going to look at this example, see if we can identify it as one of these types, and then make a statement whether the argument is valid or not. So what we do with these is we take the original argument, and we have to decide to call one of them P and one of them Q. What is P? So for this particular example, the statement P is going to be Nelson did plays. So we have this argument. If Nelson did a plays, the opponent gets shut out. The opponent does not get shut out. Therefore, Nelson did not play. So statement P is Nelson did plays. Q is the opponent gets shut out. And now we can rewrite the original argument in terms of the symbolic logic. So the first one is a conditional, which means it's an if-then statement. And I guess that should say then. So what we can do is replace this first premise with if P, then Q. The second argument, or the second premise, is the opponent does not get shut out. So we decided to have statement Q being the opponent gets shut out. So then I'd have a negation of Q to represent premise 2. And the conclusion is the negation of P, because here he does not play, here he plays. So if we write this out, we'll have if P, then Q, not Q, and then we'll draw a line, and we get not P. So we look at these and see if we can find something that looks like that. So do we see one of these arguments that matches up with what we have here? Oh, we're looking at these things here. So you can see we've got if P then Q, if P then Q, if P then Q. These are all these different ones. Here we have not Q and we have not P. So this argument is a case of modus tollens, and it says it is a valid argument. So as a consequence, is the argument valid or not? We'd say yes, it is, because of the type of argument it is. Now the problem here is, of course, the original statement is maybe not correct. So because if the opponent doesn't get shut out, then that doesn't, I mean, there are cases where if somebody else played and the opponent got shut out. So this is a kind of a inclusive statement of everything. This guy plays and the opponent gets shut out. I guess what it would say is if, I'm trying to think of the right way to do that. I mean, you can think of cases where this actually doesn't, is not true, but the argument as presented, I'm confusing myself there. I can think of cases where that somebody else would play and they would get shut out. And therefore, well, I guess that's true. Is that true or not? I guess it actually is a true argument. I was looking at it the wrong way. But it's saying that if the opponent does not get shut out, that means he doesn't play, but it also means that somebody else could have played who resulted in a shutout. Okay, so I guess it is a valid argument. That's why it's good to use symbolic logic, because sometimes you can look at these and get yourself confused. Okay, so you got a couple of those, maybe one for homework, where you have to rewrite it, look to see whether it's one of these standard type of arguments, and then make the conclusion based on that. Now we're going to do a problem where we have more than two premises. So up to this point, we've had premise, we've had the first premise, the second premise, we've had a conclusion. But you can go more complicated, which ends up being more confusing and sometimes harder to determine whether it's a valid argument or not. And so we're going to use this as an example. And you go through the same procedure, it's just you have one more premise, which you connect to the other premises with an AND statement. But otherwise, the procedure is exactly the same. You still put together a truth table. You still look to see whether the result is all trues, and you make the same conclusion based on that, the criterion that we've done before. So the argument here is Carrie Underwood sings or Joe Jonas is not a teen idol. That's the first premise. If Joe Jonas is not a teen idol, then Jennifer Hudson does not win a Grammy. That's the second premise. And Jennifer Hudson wins a Grammy. That's the third premise. The conclusion is that, therefore, Carrie Underwood does not sing. Is this a valid argument? So what we're going to do, just like we did on the previous one, is we're going to rewrite this in symbolic logic. But in this case, it's not going to be one of the standard arguments because no standard argument has three premises. So the first thing we're going to do is we're going to decide what letters we're going to use and what the statements are that represent the letters. So we typically start at P and we go P, Q, R, S, T, U, V, like that. So I'm just going to go through and pick out, as I go through here, I'm going to pick out what P, Q, and R stand for. There are three different statements that are involved in this premise, these premises and arguments. So the first thing we have is Carrie Underwood sings. So I'm going to make that statement P. So the negation of P would be Carrie Underwood does not sing. Statement Q, it says Joe Jonas is not a teen idol. I'm going to just use the positive version. It doesn't matter. You know, I could have Q being Joe Jonas is not a teen idol, but I'm going to let it be Joe Jonas is a teen idol. That will just affect my logic statement, but it won't affect the results. And the third one involves Jennifer Hudson. So Jennifer Hudson wins a Grammy. Again, you could have R represent Jennifer Hudson does not win a Grammy. This would be, it just changes some of the statements to negations and some from negations back to regular statements. So those are my three statements. Then I take the premises and I write the symbolic logic that's associated with that. So let's call this premise 1, this premise 2, this premise 3, and we'll say this is the conclusion. So we use numbers to represent the different premises. So premise 1 would be Carrie Underwood sings, which is statement P. Or, so we use the or, Joe Jonas is not a teen idol. So Q is Joe Jonas is a teen idol, so we're going to put the negation of Q to represent this statement. Premise 2 is an if-then statement. So if Joe Jonas is not a teen idol, so again, Joe Jonas is a teen idol is Q, so is not a teen idol is the negation of Q. We use the conditional sign because it's an if-then statement. Jennifer Hudson does not win a Grammy, so that's going to be the negation of R, since R is she wins a Grammy. And premise 3 is Jennifer Hudson wins a Grammy. which is just going to be R. So we've got an OR statement, we've got an if-then statement, we just have a statement. And then our conclusion is Carrie Underwood does not sing. So the conclusion would be the negation of P. So those are my symbolic translations of the original word premises and conclusions. So next what we do is we're going to create a logic statement that involves all four of these. So what it says is you take each premise and you connect those to each other with an AND. So I do the first premise and the second premise and the third premise. And those are my three premises, and I'm going to put a square bracket, and then I have it's a conditional connected to the conclusion. So that's the logic argument that we're going to look at to determine whether this is a valid argument or not. So we need to determine how big a table we need now. So since we have P, Q, and R, that means N is equal to 3. So we have 2 to the N, or 2 cubed, which is 8. And then we take 8 plus 1 equals 9. So we need 9 rows. Just like, you know, with 5, 9, what was the other one? Next one was 17, I think. The columns, for the columns we have N, which is 3. So we got 3 columns for the 3 letters. And then we need to find out how many columns we need to represent this logic statement. So why don't you count that, and we'll do a little quiz here. Okay. So it's one of these 3 choices. So how many people think 11? Additional. Yeah, plus the 3. So you got, I'm just doing 11 to represent this logic statement. Okay, how about 12? How about 13? Nobody knows. Okay, let's look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So the answer is 11. So we do it for the letters, 1, 2, 3, 4, 5, 6. Then we have 1, 2, 3, 4, 5 logic symbols. So it's 11. So plus 11 equals 14. So we need 14 columns. What's that? Yeah, 14 is the total number. So I thought I had a table somewhere here, but I'll go ahead and make it up. So let's see, I need 5 by 7. So while I'm making mine, make yours up. Oh, did I do the wrong? Oh, I didn't make it the right size. Let's try it again. Do it right this time. Okay. I need one more row. 5 by 7. There's 14. Here's 9. Okay, so that's 9 by 14. So we put in P, Q, R, and then we do our logic expression, which is going to be P or not Q and not Q. If not Q, then not R and R. So those are all my three premises connected by ands. Then I have a conditional to not P. So let me put this on one page so you can see it. So P, Q, and R, P or not Q, and if not Q, then not R, and R, therefore not P. So now we just fill out the first three columns like we normally do. Yeah, some of you tried to confuse me by doing R, Q, and P or something up here, but I didn't take off for not doing it alphabetically, but that just made me have to work harder to grade your tests. So those give us the 8 possibilities of trues and falses. Okay, so now we're going to do the 6 columns that involve P or not P, or Q and not Q, or R and not R. So here we just have P, so we're going to copy what's down from the P column, which is 4 trues and 4 falses. So now we got to do the negation of Q. So instead of true, true, false, false, it'll be false, false, true, true, false, false, true, true. Then we have the negation of Q again. So it's false, false, true, true, false, false, true, true. Then we have the negation of R. Here's R. True, false, so it's going to be false, true, false, true, false, true, false, true. Then we've got R. True, false, true, false, true, false. And then finally the negation of P, which is instead of 4 trues, it's going to be 4 falses, and then 4 trues. So those are all. Does everybody understand? See if anybody not get that. Okay, so now the question is, when you've got more than 2 premises, which and do I do first? Well, we actually have to do what's inside the parentheses first, so let's do that. So the only things we have inside parentheses are these 2. So we're going to compare these 2 columns. We have the OR statement, and the OR statement is only false if they're both false. So these are both false, 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 false. Because it's an OR statement, everything else is true. And then we do the next thing in the parentheses, which is the conditional. Conditional is only false if the first one is true and the second one is false. So that's the first instance. And we look for another one, usually 2 out of 8. So there's the second one. So we got 2 trues, and that's actually the wrong. Those should be the false ones. I don't know why I did that. Okay, true, false is false. So those go to false. So the only time a conditional statement is false is if the first is true and the second is false. All the other ones are true. Okay, now that we've got those, the question is, do we compare these 2? Actually, do we compare these 2 using this, or do we compare these 2 using that? And the answer is, or do we compare these 2 first? Well, the answer is it doesn't matter. So you can compare any of the ands in any order that you want. So because it's easier to work from left to right, I'm just going to compare these 2 columns with the and statement. I'm going to put the results in that column. So I take the center result, which is the result of this entire premise and the entire premise here. So I'm going to put my fingers on the red columns, and I have an AND statement. So the only time an AND statement is true is when they're both true. So the first case, they're both true. The second case, they're both true. Keep going down. There's another one, true. And the last one. Okay, everybody see that? True, 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 true. So the other ones are false. Which is, pardon me? Oh, those both true? No, that's a false there. Yeah, that's why it's hard. You got to be really careful. So this one's false, this one's true. So it's false. Which is kind of interesting because a lot of times when you have an AND statement, you just end up with 2 out of 8. But the thing is, this one has 6 out of 8, and this one has 6 out of 8 true. So when you do it here, you get 4 out of 8. Okay, now what we're going to do is we're going to compare the result from these first 2 premises connected by the AND, and we're going to compare that with the one remaining. And we'll put the result right there. And again, we're using the AND statement. So again, we stick our fingers on the columns, otherwise we're going to get confused. And we're going to look for the case where we have true in both columns. So I see 2 trues there, and I go down, and that's the only one. Just the first case here, true versus true. All the other ones have at least one false in them. So it's true, false, 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 false. Got one true and a lot of falses. Now this column, because I did that last, it's the result of the entire left-hand side. So we're going to compare this column now with the column on the right-hand side of the if-then statement. That's the last thing we do. And the results will go in here, and we'll use the if-then statement, the rules for the if-then statement. So now I'm going to put my finger on this column, and I'm going to put my finger on that column. And what I'm going to look for is any cases where I have true for the first entry and false for the second entry. And that's the only case where an if-then statement is false. So that one is false. First one's false. You can see that all the rest of them have the first term being false. So there's not going to be any other cases of true than false. So these are all true. And you think, well, 7 out of 8, that's pretty good. Well, that doesn't work. Okay. So this is my result. And what we can say is, since the final column was not all trues, we do not have a tautology that's right, yeah. And the argument is not valid or invalid or a fallacy. So those are all words we can use here. Or a fallacy. So, if you look at those original arguments and try to think through all those possibilities, your mind cannot, there's no way your mind can keep track of everything. But by using truth tables, it's a fairly straightforward procedure. I mean, it's laborious, but it is doable. And let's see, somebody's dinging. So, oh, I don't know what that was about. Okay, somebody's dinging. So that's how you handle. You got a couple of problems. How you handle problems where there's more than two premises. Same procedure, you just have one more premise. You have a bigger table. You have usually more arguments or more statements, but besides adding more, the complexity is not that much more. It's just a longer problem. So what we're doing is you identify the statements, you convert to if-then statements if necessary. Sometimes the if-then statements are not explicitly if-then. So if you don't see a if-then, you might have to rewrite it. You write the premises and conclusions of symbolic logic. You determine whether the argument is valid using truth tables, or the table at the bottom of page 128, which is the green thing I showed you earlier. So if it's one of the standard arguments, you can just use that table and say it's a standard valid argument. I'm done. Or if it's not one of the standard arguments, then you can do a truth table and see what you get. And if you get all truths at the end, then you say it's a tautology, therefore the argument is valid. There's my table. I knew I had it somewhere. Let me just delete it for right now. Oh, there's my answer. Should be the same as I got here. Yep. False, true, 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 true. So one little false. Okay, the last thing we're going to talk about is arguments of Lewis Carroll. So Lewis Carroll, it's in the book, there's an example which I'm just going to read. And what it does is it uses the transitive property over multiple premises. So many premises that it kind of looks ridiculous at the end. So this is the example they give. For the want of a nail, the shoe was lost. For want of a shoe, the horse was lost. For want of a horse, the rider was lost. For want of a rider, the battle was lost. For want of a battle, the war was lost. Therefore, for want of a nail, the war was lost. So what I mean, theoretically, that's true. You know, all these things could be connected, and ultimately the war could be lost just because you didn't have a nail for a horse. Now, the probability of that being the cause of losing the bat war is pretty small, but it is a possibility, and it is a valid argument because each statement is connected to the next statement with an kind of an if-then statement. Now, sometimes when you're given these kinds of arguments, it isn't something where you can just kind of cancel things out. So, for example, here's the classical. Here's an example of a three-premise Lewis Carroll type argument. So what you have is if P, then Q, if Q, then not S, if not S, then R. And from these three premises, because they're all if-then statements, and because the Q is here and there, you can kind of cancel them out, and the not S is here, and the negation of S is here, and the negation of S is there. You can think about canceling them out. And it's like if A equals B and B equals C and C equals D, then A equals D. It's kind of, that's the transitive property of mathematics. And therefore your conclusion is you can take the first statement in the first if-then statement and the last statement in the last if-then statement and connect those directly. So if P, then R. But sometimes they don't come exactly in the order that makes it easy to cancel them out. So what you do is you can use this contrapositive. And the way I'm going to explain that is if instead of being given that, well, let me unerase it so I can make sure I do it correctly. Let's say the original argument was that instead. So the problem, if I had this argument, you'd say, well, I can't cancel out the Q's because I've got a not Q and I've got a Q, and they're on different sides of the if-then statement. So this doesn't nice and neatly fit into the format we just looked at. But you can use the fact that the contrapositive of a conditional statement is equivalent. They're equivalent to each other. So what I would do in this case is I would say, well, I could take the contrapositive of this statement, which is where you switch the S and the Q, and you make the ones that weren't negated, and the ones that were negated, non-negated. So the negation of a negation is just that. So this is the contrapositive of this statement. So then, because they're equivalent to each other, I can take the original statement that wasn't very helpful, and I can substitute in the contrapositive, and then I get back to where I started, which was where I can conveniently cancel out the intermediate things. So let's look at an example. And here's the procedure. Write each premise using symbolic logic. Choose a premise that contains a statement mentioned only in one premise. That'll be your first statement. Order the statements to use the transitive property. Use the contrapositive of a premise if necessary to achieve the goal set out in step 3. And write the conclusion in symbolic logic. This is in your book. I just rewrote it. Let me tell you what page it's on so you don't have to write it all down again. Or did I write this? Maybe I made this up. Actually, it looks like I made that up. Okay. So that's the procedure you go through. So what I'm going to do, we're going to do the next example, and we're going to just follow the steps. So here's, let's see, this is problem number 50 in your book. So just write problem 50. And they actually tell you what letters represent what statements. Statement P is one is able to do logic. Statement Q is one is fit to serve on a jury. Statement R is one is sane. And statement S is he is your son. What we have are 3 premises. So given these 3 premises, what is the conclusion using this procedure? So the first thing is write each premise using symbolic logic using if-then. Notice there's no if-thens in here, so we have to rewrite these statements as if-then statements. So the first thing is I'm going to rewrite these as if-then statements. Everyone who is sane can do logic. So how would I write that? If one is sane, then one can do logic. And now we'll look up here and see if we can come up with a symbolic or some of these letters to represent the different statements. One is sane. One is sane. Okay, that matched up pretty easily. So this part here is statement R. And then we connect it with the arrow because it's an if-then statement. One can do logic. One is able to do logic. So that's pretty much the same thing. So the first statement written as an if-then statement and then converted into symbolic logic. So that's A. Statement B is no lunatics are fit to serve on a jury. So what is a lunatic? Using some of these, which letter applies to lunatics? Yeah, one is sane. So the negation of one is sane is one is insane. One who's insane is a lunatic. Okay, so you could rewrite this as you could say if one is a lunatic, then 1 is not fit to serve on the jury. It's not fit. So no lunatics. It's kind of like the same thing we did here. Everyone. We didn't use everyone. We just said if one is sane. That means everybody. If you're sane, then if you're that everybody, then you can write it as one is sane. Okay. So if one is a lunatic, then one is not fit to serve on the jury. Okay, so if R is one is sane, then if one is a lunatic would be the negation of R. So this statement here is the negation of R. And one is not fit to serve on a jury. Q is one is fit to sit on a jury. So it would let me move this down a little bit. So we've got not R. This part, one is not fit to sit on a jury, is going to be the negation of Q. So we're going to have if the negation of R, then the negation of Q. So that's our second premise. First converted into an if-then statement, and then converted into symbolic logic. The last one is none of your sons can do logic. So we could say if one is your son, then one, or they, I'll say they cannot do logic. Okay, so it's into an if-then statement. Now we need to choose the proper letters. So what was he is your son? That's the same as one is your son. So this first bit here is going to be S. So this little bit is S, statement S. The second one is they cannot do logic. So we go up to the statement, so we say one is able to do logic. So if one is not able to do logic, then that would be the negation of P. So that's the negation of P. So again, we can rewrite this as an if-then statement, which would be if S, then the negation of P. So those are the three logic statements. This one, and that one. So we've done that. So let's write them down now because we're still working on part one. So we're going to write down the three logic statements. First one is, or three premises. If R, then P. The second one is, if not R, then not Q. And the final one is, if S, then not P. Now I have to decide which one we want to do first. So you look for a statement which contains only one, or a statement that's only mentioned once. So let's just write the P, Q, and R. So let's just go through and do an inventory, and it's either P. It can be either P or the negation of P. So here we have one mention of R. We have one mention of P. We have not R. We have not Q, so we can put that in the Q column. We have, I forgot S. We have S. And we have not P. So you can see that Q is mentioned one time and S is mentioned one time. So we can choose either one of those to be the first premise in our argument. So which one am I going to choose? Let's choose this one because it starts out with S instead of the negation. Now, what I need to do is find an argument that starts with not P, so I can cancel them out. So I go up here and I look, I don't have any that don't have not P, but I can write the contrapositive of this one. So to do the contrapositive of this argument, you switch P and R, and if they're just the statements, you make them negations. So I can make that into not, if not P, then not R. That's equivalent to if R, then P. So I'm going to use that. I'm going to use this red statement here to make the next thing. So it's going to be that. And then my final statement has to be not R, then something. Well, I already have that. That's already in, it's already made up. So I can just write that off directly. And what I've done is that I've ordered them so that I can cancel out these intermediate steps. And therefore my conclusion is I take the first part of the first premise and I write the last part of the last premise. So now I've done all that symbolically. I can go back and just rewrite it here. So S is if he is your son, then not Q. Then he is not fit to serve on a jury. And so this is a logical conclusion based on these three initial premises. Looking at it initially, you're thinking, it's hard to connect them all together. That's why you have to convert it to symbols and rearrange them symbolically and then come out with something that is a valid result. So again, let's review what we did here. We took the three premises, first made them into if-then statements. Then we replaced them with symbolic logic. We took the three premises, which weren't in the correct order to allow us to use the property of transitivity, and we decided to make the first statement. There's two options. We could use this as the first statement, or we could use this one, but take the contrapositive of it. I might show you how to do that, just show you the other options. So there's two arguments you can come out of this with. One is going from here to here, and the other one's going the other direction. So because I chose this as my first statement, I knew that I needed a negation of P here, but I didn't have it here, so I used the property of the contrapositive being equivalent. So I switched these and made them negations, and then I could use that in there so that it canceled out. And then I saw that my remaining statement that I hadn't used already had the negation of R already in the right place. So I could just write that down, and then I took the first part of the first statement, the last part of the last statement, and make that my conclusion. So let's do the other one just to show you what the other equivalent would be. And that would be to start with, if I took the contrapositive of this thing, I would switch Q and R. So Q would become the antecedent and R would become the consequent, and I would take the negations off. So here I put the negations on, here I took the negations off. So I would use this as my first statement, which would be if Q, then R. And then I would say, oh, I already got the second part. I need something that has if R, then something, so I can cancel these out. So I've used this one, and I've used that one. The only one I have left is this. And I'd say, well, the problem with this one is I have S, if S, therefore not P. What I need is the other way around. So I would take this and I would switch P and Q. and the negation of P would become P, and S would become the negation of S. So that would be the one that I would use as my final one. And in that case, these cancel out, those cancel out, and my conclusion would be if Q, then not S, which is the contrapositive of what I got going the other direction. So you can see I could rewrite this as what I got in the first case. So it doesn't give me a different answer. It gives me the contrapositive of the answer. So let's just, what is the contrapositive? So these are equivalent to each other. But let's write the statement that associates with that. You would say 1 is fit to serve if one is fit to serve on a jury. Then he is not your son. So that would be the other way of, that's also a valid argument. So if you found somebody, if they said, oh, next person in is fit to sit in the jury, you'd say, well, obviously it's not your son, because he would have never gotten in if it was your son. So they are equivalent to each other. And that's your homework assignment for the last section. So there's two Lewis Carroll, 49 and 52 are Lewis Carroll thingy-diggies. 29 and 33 are arguments with more than two premises. And the rest are just using truth tables to find out whether arguments are valid or invalid. Yeah. So we have another debate coming up. I think Caitlin's the only one that's been watching them. I mean, there's really no, it's interesting. I mean, basically, you've got the people who are strongly in favor of voting for Hillary. They're not going to change their mind. You got the people who are going to vote for Trump. And then there's the people in the middle, which is not that many people. Most people have made up their mind at this point. Well, this weekend they had Rudy Giuliani, who's the former mayor of New York City, on, and they asked about the sexual assault charged comments about Trump. And the person asked him, have you read the articles about their accusations? Are you familiar with what is behind the accusations? And basically he said no. So he didn't, I don't think he wanted to read them, because if he read them, then he would have to say, it sounds like it's a valid argument that he did do something. So if you don't read them, then you can deny that they happened. Oh yeah, he's one of his main surrogates. He and Chris Christie and who else is and then of course the official spokespeople for the whole thing. Huh? Mob up. Who did? Oh, Giuliani. Yeah. Yeah, I mean, Giuliani did some good things. He's just, I'm not sure what his, I'm not sure what he's trying to get out of the whole thing. The Trump, he wants to be a commentator on the Trump network, maybe. That's Giuliani, because he needs a job. So he probably wants a TV job. Because I know these guys, they know. They're not idiots. He has not. Pardon? Does he know? That's true. I don't know if he knows that or not. The most disturbing thing I have about Trump is this rigged election thing, because that's dangerous. It's also un-American. So it's also interesting about Hillary. So on the Hillary side, you've got the release of the transcripts of one of her speeches to Wall Street executives. And it's interesting. It's the people on the left probably don't like it, but they're not going to vote for Trump. They may not vote at all, but they're not going to vote for Trump. The people in the middle, it actually makes them a little bit more probably comfortable with Hillary, because they know that she's not as left-wing as she had to be to win the primary. So, she's more pragmatic than you might be led to believe. Which I always figured that was the case. You have to. Sometimes you have to say things in the primary to get elected, which you don't 100% agree with. It's just the way the system is these days. So, anyway, I'll be glad when it's over. I guess I'll be glad when it's over. If Hillary wins, I'll be glad when it's over. Huh? Yeah. Yeah, I'll probably get in trouble. I'll be locked up. I'll be jailed like Hillary will be. Hate anybody. I was telling that this morning. I said, I don't really hate Trump. I don't agree with Trump. I think Trump is dangerous, but I don't hate him. Pardon me? Do we have to do geometry? Yeah, it's in the course description. So let me explain how we're going to do geometry, because we're going to do this in like 2 weeks, and you've had geometry for a whole year. So we're not going to do any proofs. We're basically going to do two things. We're going to refresh you about the terminology used to describe various geometry things, like lines and angles and squares and rectangles. And we're going to talk about some key rules for figuring out, if you know some angles, how to calculate a third angle. Know two angles in a triangle, how to calculate the third angle. We're not going to talk about law of sines and law of cosines and stuff you might have learned in pre-calculus if you did pre-calculus. So it's pretty much for people who are becoming elementary school teachers who would have to teach some geometry at a elementary level, but nothing near what you learned in geometry in high school. So you should be okay. So we have to slog through some terminologies, and that's all I can do. I have to cover it, so here we go. So the first section is talking about points, lines, planes, and angles. And pretty much in this section, it's about terminology. So this is a table in your book, so you don't need to write it all down. Just refer to it. So, and I'm going to emphasize the things that I think are more important that I've seen used. So it's interesting. I looked up the definition for line, and it's really confusing. Most people know what a line is. It's one of those straight things. You use in the definition of line, you use the word line, so it's sort of circular. So when you actually do use the exact mathematical description. It uses these big long words, but you pretty much know what everybody knows what a line is just from the graphical representation of what that is. The key things that you have to remember about lines is that a line doesn't have a beginning and end. It goes off to infinity. If it's a line of a fixed length, that's called a line segment, which we'll cover here in a second. So, I mean, we normally think of that would be a line, but that's technically a line segment. And to define a line or any of the other things that look kind of like lines, like rays or line segments, you have to specify 2 points. And the points are determined or represented by letters. In our case, we're going to use capital letters. So in this figure, you see a line with arrows on both sides. That's to indicate that a real line goes on forever in either direction. And I'm going to use letters A and B to specify this line. Now if I were to put a point here, which was point C, and a point here, which is point D, I could also, this would also be the same line. So there are an infinite number of combinations of points that would define a line. So in this case, we're just using points A and B. Because it goes to infinity in both directions, it doesn't matter which one you put first, because it still defines the same figure. So whether I have AB or BA, I'd still draw the same graphical representation of what a line is. One thing is lines do not have a thickness. We have to draw a thickness because we can't draw a line without thickness. So, but a real mathematical line has no thickness. It just has points, which points also don't have any dimension. We make them so we can see them, but a real point is infinitesimally small, but we draw it as a dot. Okay, so that's a line. Half lines, we don't really use that much. So let's talk about rays first, and then we'll tell you the difference. So for rays, it is important what the order. It's kind of like coordinate pairs versus sets. So for lines, the order is not important, but for rays, it is important because one letter represents where the ray starts, and the second letter represents a point through which any point through which the ray travels. So again, if I put another point here, which I call point C, I could have ray AC, and that would be the same thing in space. So the first letter could not change because it's just A. So the first letter would not change, but the second letter could change depending upon whatever I choose to be that point that defines enough of the line or enough of the ray to be able to draw it. So the key thing to remember here is for rays, the order is important. You always put the beginning of the ray as the first letter, and the second letter represents another point on that ray. So these two rays are different even though we're using the same 2 points. This one starts at A and goes through B, this one starts at B and goes through A. And this one goes to the right to infinity, and this one goes to the left to infinity. They use a little dot here to represent that it's a ray. A half line is the same thing, except you don't include point A. So it's like it's infinitesimally close to A, but not exactly at A. These aren't used that much, so I won't even test on it. So know what a line is, know what rays are. And finally, you have a line segment, which is, again, the order is not important because it doesn't go off to infinity in just one direction. It goes between these 2 points. And A and B represent the points that are at the extremities of the line segment. So if I put another point in here, I couldn't use that to define the line segment. It has to be the ends of the line segment define it, and the order is not important. So those are our different ways of that thing we call a line. Line goes both ways to infinity. a ray starts one place and goes that way or goes that way. A line segment is just has a finite length to it. What I will ask you to do is I will give you, and you've got a problem like this in the book, the problems, what I will do is I will give you some kind of thing that looks like this, and then I will put some letters along here. So let's say this is X, W, W, X, Y, Z, and I'll say, what will I say? Yeah, I forget how this goes. Let me think about this. Yeah, I can't remember the exact details. I'll probably do this in the next page or so, so we'll come back to that. Okay, so what else can you do with lines and rays and line segments? Well, the main thing here is, first thing is you can create angles. So an angle consists of two rays starting at the same point. So we have ray BA and we have ray BC. And where the two rays, the common point from which the two rays start is called the vertex of an angle. So we're talking about here, we're talking about angles. So this side is going to be ray AB, or BA. This side is going to be ray BC. And when you connect these two rays together at B, then you get this thing that's an angle. So this is your angle. So does anybody remember how you represent an angle from geometry? So what you do with an angle is you specify 3 points to specify an angle. So this particular angle that we have, we would show, you would use that symbol. It's like somebody's nose, but it's, put a little head on there, or a beak. Anyway, it's you show the angle, and in this case, we would have letter A, B, and C. The center letter is the vertex of the angle. So what if I did it the opposite way? If I had angle CBA. Again, this is your vertex, the middle one. Would that be any different? No, because you've got ray AB, you've got ray BA and ray BC, and it doesn't matter which way you do it, you're still going to have the same angle. So in terms of an angle, whether this is first or that's first, doesn't matter. The important thing is that the vertex is the center letter. So this angle here, this middle one, would be angle BEF or angle FED, DEF or FED. They're the same thing, but they both have E as the middle point. Over here we'd have angle JKL or angle LKJ. Does anybody remember what an angle is? What kind of angle is between 0 and 90 degrees? Greater than 0 and less than 90. Acute, yeah. Okay, so we talked about specifying angles. This X point is interior to the angle because if you extend these out, it's inside the angle. The value of the angle, remember, if you take this ray, the second ray, and you just rotate it all the way around and come back to the original ray, that goes 360 degrees. So if you go halfway around, that's half of 360, which is 180. And if you go around a quarter of 360 is 90. So this angle is 90 degrees. If I drew an angle, a ray that was the same orientation as this, I would get here. So you can see this angle is less than 90 degrees. And this one, if I drew a line that's 90 degrees, this one's more than 90 degrees. So an acute angle, and let's just use x to represent the acute angle. X is going to be where the value of the angle is greater than 0 but less than 90 degrees. Then you have a right angle. A right angle, which I'm going to call x again, is when x equals 90 degrees. And then you have, what's the one that's between 90 and 100 degrees? Obtuse. Yeah. So the other obtuse angle that's where the angle is greater than 90 but less than 180 degrees. Does anybody know what it is when the angle is equal to 180 degrees? Straight angle, right? Well, yeah, I mean a straight angle is a line, except you probably have 3 points instead of 2 points, because you'd have the middle point, the vertex of the angle would be specified. So that's the only difference between a line and a straight angle. Well, it's really two rays connected that way. So you got, yeah, so that's the difference between a straight angle is 2 rays, whereas a, pardon me? Not really. Now, if the angle is greater than 180 degrees, then you go back and you just measure the angle the other direction. So we don't have anything where the angle is between 180 and 270 or between 270 and 360. Okay, so those are those things. What else can we do here? Okay, we just talked about that kind of stuff, so we can skip over that. Yeah, so here are some, these are out of your book. So this angle would be a 0-degree angle. I don't think there's any, I don't know if there's a special name for that, because what we have are 2 rays. We have ray BA and ray BC, and they're right on top of each other. So in this case, we would have angle ABC, and that's equal, has a measure of 0 degrees. And then as we rotate this second ray counterclockwise, we increase the angle. Wherever we stop is the value. In this case, we stopped before we got to 90 degrees, so this would be, this angle in this case would be an acute angle. This one is 10 degrees, so this one would be also an acute angle. This is an acute angle. This is a right angle. This is an obtuse angle. This is, I don't know what the heck they call that one. It's one where you go all the way around, you're back to where you started. So it's basically the same as that in space. But okay, so that's just demonstrating the different kinds of angles that you have. Talk about measuring angles. The way you measure an angle is you take the vertex, you put it at the center of the protractor. You have one side of the angle along this line, and then you look at the extension of the second ray involved in the angle, and you see where it intersects the protractor, and you measure it off. You guys know how to do that. Okay. Now, these are important things to know. Okay, the terminology for these. So when you have two straight lines that intersect, the resulting angles associated with those two lines intersecting have special names. Now, you can represent the measure of an angle by just putting the measure, meaning the value. Is it 30 degrees? Is it 50 degrees? You can just represent it without a number by just putting a single sweep. And if I do the single sweep over here, what that's telling me is that these two angles have the same value. Now I've got two other angles associated with these two intersecting lines. And if I use two little sweep things and I use them on both sides, what I'm showing is that these have the same value. I don't know what the value is, I just know that they're the same. So the rule here is, well, so which angles are vertical with each other? There's some noise there. So let's look at the angles. We have angle Q, and this thing's, I guess, the letter M, QMR, which is this angle. And the angle that's opposite, which would be angle NMP, are vertical angles. Also, you can look at these other two. You got angle QMN, and angle on the other side is RMP, are vertical angles. So they have, basically they are, when you have two lines that intersect, you have two angles that are opposite each other, and those are equal to each other. And you have two other angles that are opposite each other, and those are equal to each other. And those angles are called vertical angles. I'm going to skip that problem right now. Now, what is the, if I say, let me ask for our last question here, is if I took the measure of angle QMR and I added it to the measure of the angle QMN. So this is QMR, this is QMN. What is the value for that angle? The sum of the two. Did I hear somebody say it? So vertical angles are equal to each other. These adjacent angles, this angle and this angle, add up to 180 degrees. Because if I go to here and then I go all the way around there, I'm going halfway around. So I have a straight line, and the straight line, or it's not really a straight line, it's a straight angle. The angle for a straight angle is 180 degrees. And what's the name of two angles that are, when added together, add up to 180 degrees? Do you remember what kind of angles, what that's called? The two, they have a special name that relates those two angles. It starts with an S. Supplement. So there's supplemental angles. So two angles that add up to 180 degrees are called supplementary angles. We'll talk more about that on Wednesday. I'll hand the test back on Wednesday too.